Hello everyone, you're welcome back to our SURD class. In the previous class, we introduced SURD. We gave some of the rules governing SURD. We discussed briefly about rational and irrational number, and we also looked at some questions on simplification of SURDs. So if you want to know all these, you go back to the previous video and watch before you join us. But if you have done that, let us continue from where we stopped. Today we are going to start our discussion on addition and subtraction of SURDs. Addition and subtraction of SURDs. You will remember that in the last class when I introduced SURD, I made us to know that SURDs can only be added or subtracted one from another if and only if they are similar. And when a SURD is said to be similar, it means that they have the same irrational number. So for SURDs to be added, they must be in the same basic form before you can either add or subtract. Some SURDs might look as if they are not similar because they are not in its simplified form. So sometimes there may be need for you to simplify such SURD before either adding or subtracting. We will understand the true examples. So let us give few examples to be able to explain what I mean. If you ask, for instance, to evaluate root 32 plus 3 root 8. At the first look of this expression, one would say that you cannot add these SURDs because they are not having the same, or they are not similar. They are not similar because the number and the roots are not the same. But you can actually confirm truly if they are or not only if you simplify the SURDs and make sure that the number and the roots are, or the SURD is in its simplest form, such that you have the number and the root to be an irrational number. So how do we do that? You remember in our last class we were able to simplify SURD. So we can easily simplify SURD now. And I said that in order to do that, you should first of all have at your memory or write down somewhere perfect squares. And how to get perfect squares are the square of integers, positive integers. The square of 1 is 1, the square of 2 is 4, the square of 3 is 9, the square of 4 is 16, the square of 5 is 25, the square of 6 is 36, the square of 7 is 49, the square of 8 is 64, the square of 9 is 81, and the square of 10 is 100. Let's stop here. So what we will do is to look for any number here that can divide 32 without remainder. 4 can do that. 16 can do that. I think these are the only two numbers here, aside 1, that can divide 32 without remainder. And remember I told you in our last class that it is preferable to use the highest perfect square that can divide the number. So between 4 and 6 and 16 is higher than 4. So it is preferable for us to use 16 to divide 32. That means that root 32 plus 3 root 8 can be expressed as root 32. If you divide 32 by 16, you will have 2. So 32 can be replaced with that 16 and 2, because 16 times 2 will definitely give you back 32. Then plus 3 root 8. But root 8 can also be splitted. Look for a perfect square amongst what we have listed that can divide 8 without remainder. And if we look at that, you see that 4 is the highest possible perfect square that can divide 8 with a remainder. When 4 divides 8, you have 4 by times 2. And when you see that, you can see again that 16 is a perfect square. Because of that, the square root of 16 is 4, we know. So we have 4 root 2 plus 3. The square root of 4 is 2 times, you bring out that 2, because if you find the square root, it's no longer going to be inside the root. 2, then root 2. And to simplify further, we are going to have 4 root 2 plus 3 times 2 will give you 6 root 2. And you can see now that those two numbers that we thought are not similar are now similar, because we have been able to simplify root 32 to be 4 root 2 and simplify 3 root 8 to be 6 root 2. And now you can see that they have similar irrational numbers, and because of that, they are similar sorts. And when sorts are similar and you want to add, what you are simply adding is the rational numbers, the 4 and the 6. It's just like saying 4x plus 6x. You know you are going to just add 4 and 6. So you take this as a variable. If you don't actually understand, you can assume this as a variable in order to add. So when we put this together, we're going to have 4 plus 6, and that will give us 10 root 2. It therefore means that root 32 plus 3 root 8 is equals to 10 root 2, and we have been able to solve this to get it right. Okay, let's solve one more question before we forge ahead. If we look at a question where you are asked to evaluate 2 root 12 plus 3 root 48 minus root 75. Of course, this is containing both plus and minus. It's still the same thing. You must not write down those numbers, those perfect squares. But to be on the safer side, you can write it down somewhere and be looking at them. So, if having it somewhere, assume we have it somewhere, we have that 2 root 12 plus 3 root 48 minus root 75, like we said earlier, you can see they are not similar for now, but we have to make sure that they are all in their simplest form before we can actually conclude that if they are similar or not. So this is going to be equal to 2 root 12. And amongst the perfect square, which of the perfect square can divide 12 without remainder? Remember, we have 1, 4, 9, and so on and so forth. 4 can divide 12 without remainder. 9 cannot, and of course every other number perfect square is greater than 12, so it is only 4 we can use. When 4 divides 12, you have 3, so 4 times 3 is going to give you 12. You see that? Plus 3 root 48. Instead of root 48, a perfect square that can divide root 48, 4 can divide 48 without remainder. But let's do for another one. Which other one? Can 16 divide without remainder? And 16 can as well go. 16 can actually divide 48. And if 16 divide 48, we have 16 times 3 is 48. Why am I not using 4? Because 16 is greater than 4. I said the highest possible perfect square is preferable. You can use 4, but you will have to do it twice in order to actually simplify it to its lowest end. So when you now go further, root 75. What is the perfect square that can divide root 75 without remainder? 4 cannot go, 9 cannot go, 16 cannot go, but 25 can go. And if you begin to go further, you see that no other number can go apart from 25. So if 25 divides 75, you will have 3. So 25 times 3 is 75. You have seen how I've broken this down to this form. So if we do that, this is going to be equal to 2 root 4 times 3. Root 4 is 2, so you bring it out, it will be 2 times 2 root 3. You go again, the second one, which is 3, of course, plus 3, then root 16. The square root of 16 is 4, so it's 3 times 4 root 3. Remember, there's still 3 inside here. And then if you go there, you will see what is the square root of 25. The square root of 25 is 5, so you bring it out, 5 root 3. So looking at this, we see that now the irrational numbers that it has are similar. So the surd is the surds are similar surds. So if we proceed, 2 times 2 you have 4 root 3, plus 3 times 4 you have 12 root 3, then minus 5 root 3. Because they are similar, I said you just add the rational numbers. This is going to be equal to 4 plus 12, 16. Minus 5, you have 11 root 3. And you are done with that. So this is how we add or subtract one surd from another. You can only do that if they are similar. Remember, if they are not, you cannot add or subtract surds that are not similar. Now let us try our hands with multiplication and division of surds. Remember, in mathematics, subtraction goes with addition, multiplication goes with division. In every topic or in mathematics, just note that whatever principle that works with subtraction most times work with addition. Whatever one that works with multiplication works with division. So in multiplication and division of surds, whether similar or not similar, can be multiplied or one dividing another, unlike in addition and subtraction that needs to be similar before that will happen. So if you are asked to simplify root 45 times root 28, okay, one can actually decide to say that root 45 times root 28 is equal to root 45 times 28. But I don't advise you to do this, because when you do this value is going to be very large, and it will be very difficult for you to actually extract the perfect square in it so that you can simplify or reduce it to its simplest form. So it is advisable to reduce them individually to their simplest form before you multiply. So that means we are going to look for a perfect square that can divide root 45. And when you have that, 9 can actually divide root 45, because 9 is a perfect square. We have, remember, I keep on reminding us, we have 4, we have 9, we have 16, we have 25, we have 36, 49, and so on and so forth. So 9 can divide 45. When 9 divides 45, you have 5. So we can actually use 9 times 5 to represent 45. Then times 28. 28 can be divided by 4. I think that's the only perfect square that can divide 28 without remainder. When you get to the higher ones like 9, 16, they will not be able to do that. So when 4 divides 28, you have 7. So I can say 4 times 7 is 28. So looking at this, the square root of 9 is 3. So we have 3 root 5 here, times the square root of 4 is 2. We have 2 root 7 here. So how then do we multiply? All you need to do is to multiply the rational numbers and also multiply the irrational numbers. So we are going to have 3 times 2, then root 5 times 7, according to the rules of multiplication that we had earlier. So when that is done, this will be equal to 3 times 2 is 6, then root 5 times 7. You can see that the two numbers we have are irrational numbers. So when you multiply it, it's still in its simplest form. They will still be irrational. So 5 times 7 is what? Is going to give us 35. And so you can see how we can actually multiply one surd to another. We can also do that in division. So let's look at number 2 question which you are asked to evaluate. You are asked to evaluate root 24 all over root 50. How do you do that? I said you can actually first of all rationalize before dividing, or divide before rationalizing. Whichever one is easier for you is accepted. So if I decide to rationalize before dividing, I can say, what is a perfect square that can divide 24? 4 can divide 24 to give us 6. So 4 times 6 is 24. What is a perfect square that can divide 50 to give us a whole number? 5 25 can divide 50 to give us a whole number. 25 divided 50 will give you 2. So 25 times 2 is also 50. And so you have this. And then you simplify further. The square root of 4 is 2. You have 2 root 6. The square root of 25 is 5. You have 5 root 2. So with this, we can now divide the irrational ones and as well divide the rational ones. So that will be equals to 2 root 6 all over 5 root 2, and it can be written as 2 over 5 root 6 over 2, and that can as well be written as 2 over 5. Of course, this 5 cannot divide 2, so you leave it like this. 6 divided by 2, you have 3, so you have root 3. So the answer to this question is 2 root 3 all over 5, and you are done. But if one decides to divide before rationalizing, where you remember the question is root 24 over root 50. To divide before rationalizing, you can write this to be the root of 24 over 50. And when you do that, of course, 2 can go. 2 can divide 24 to have 12. 2 can divide 50 to have 25. And they cannot divide again. So I can now say, separating them, it will be root 12 over root 25. And 25 is a perfect square. So I can just say that this is root 12 over 5. But 12 has not been simplified because there is a perfect square in 12 that can actually a perfect square in 12 that can actually be extracted. 4 is a perfect square that can divide 12. So root 12 can be represented or replaced with 4 times 3, root 4 times 3 all over 5, where root 4 is 2. So I have 2 root 3 all over 5. You see, we have the same answer, and this is shorter than the previous one. So we can as well take this option. Then let's now look at rationalization of SURD. Rationalization of SURDs. When we talk of rationalization of SURD, we are simply concerned with the process of removing irrational numbers from the denominator. Removing irrational numbers from the denominator. If I have a SURD, say a over root b, this SURD cannot be left like this. Therefore, we have to rationalize it to do something to make sure that root b, that the denominator does not carry the root. There could be root at the numerator, we don't have a problem with that. But for a SURD to be written, to be rationalized, this root at the denominator should be removed. So if you're solving any mathematics and after solving, your answer contains roots in each denominator, you have to rationalize in order to eliminate that root. So to do that, let us look at simple example that will help us understand that. If you are asked to simplify 7 over 5 root 3. 7 over 5 root 3, because root 3 is at its denominator, we rationalize by multiplying both the numerator and the denominator by the conjugate of the denominator. And the conjugate here, I mean, remember I said is a number that you're going to multiply with another number of the same integer to remove the irrational number and make it rational. So what is the number that we're going to use to multiply root 3 to make it a rational number? If you multiply root 3 with another root 3, you will have 3. So we are going to say, in order to rationalize this, we have that 7 over 5 root 3 to be rationalized is to multiply both the numerator and the denominator of this expression by root 3. So you have root 3 over root 3. And that will give us what? 7 times root 3 is 7 root 3 because they are not similar. So they will remain like that. 5 here is written root 3 times root 3, you know that it is going to be root 3 squared. And when it is root 3 squared, the square root will cancel the square. And we will have 7 root 3 over 5 times 3, because this is no longer root 3 but 3, and that will give us 7 root 3 all over 15. We have been able to rationalize this. So it means that mathematically 7 over 5 root 3, if you punch in calculator, you get the same answer as when you punch 7 root 3 over 15. As simple as that. So we have been able to rationalize this because the denominator is now a rational number, no longer a SURD. One more example in rationalization. If I have evaluate 2 over root 3 plus root 2, you see that 2 over root 3 plus root 2 can be rationalized by multiplying both the numerator and denominator by the conjugate of the denominator. And the conjugate of root 3 plus root 2 is root 3 minus root 2. Remember we said that once you change this plus to minus, you have written its conjugate. So you multiply both the numerator and denominator by its conjugate. So you have root 3 minus root 2. So when you do that, you know how we multiply. Use this to multiply this, and then here you use this first one to multiply both, use the second as well to multiply both. So when you say 2 times root 3, you have 2 root 3. 2 times minus root 2, you have minus 2 root 2 all over root 3 times root 3. Remember, when you multiply similar SURD, the root goes exactly the same SURD, because this times this will give you root 3 squared, and the square root will cancel the square. So just note it anytime you have such. So root 3 times root 3 is 3. Root 3 times minus root 2 is minus root 6, because 3 times 2 is 6. Root 2 times root 3 is root 6. And then root 2 times minus root 2 is minus, since it is 2 and root 2 will give us 2. So when you have done that, this is equals to, of course, you have 2 here. You can factor out the 2, and in the bracket you have root 3 minus root 2. Then your denominator will be, because this is minus root 6 and this is plus root 6 will subtract minus root 6, and we are left with 3 minus 2. And then when you simplify further, you have 2 into root 3 minus root 2 all over 3 minus 2, 1. And when your denominator is 1, that fraction is a whole number. So therefore 2 over root 3 plus root 2 is simply rationalized to be 2 into root 3 minus root 2. So if you have this in a calculator and also have this, you get the same answer, and this has been rationalized to give us this. So we have been able to rationalize this. We will stop here for now because of time. We will continue in the next class. In the next class, we will look at further examples. We might pick some questions in WAEC so that we'll be able to see the kind of challenges that we might face in external examination and even internal examinations on SURD, because these are just the steps and the subtopics we have under SURD. But when it comes to application, when it comes to writing exams, there might be extremes to that. So we're going to look at questions that can or we might expect in exam, so that we'll see how do we tackle those questions. Thank you, and see you in the next class. Don't forget to share, subscribe if you've not done that, and look out for our next videos.